Today we will learn how to represent factoring special products geometrically. But first I want to remind you a little bit about area. So suppose I wanted to find the area of this square. Notice it has side lengths A. All four side lengths are A. So to find the area of this square, I multiply A times A, so I'd have the area of the square is A squared units squared. Now if I want to find the area of this rectangle, I would do a similar thing. I multiply this dimension by this dimension. So I would have that the area of this rectangle is just A times B squared units. This comes in handy when I want to model factoring the trinomial a squared plus 2ab plus b squared, because I can actually represent this entire expression, this trinomial, as a sum of areas. For example, I could represent the quantity a squared by a square with side length a. Similarly, I could represent the quantity AB as a rectangle of area AB. So here's, notice I have A squared represented, 2AB, and 1B squared represented, since the area of this little square would be B squared. Now, having a geometric representation of this trinomial is extremely helpful to model factoring, because what I can do is I can essentially rearrange these four areas into a square, into a complete square here. Okay, so I basically dragged this this area A squared over here, this rectangle AB here, and this rectangle AB here, and then I completed the square by putting this B squared here. Okay, so notice, what is the area of this new square? Well, each side length measures A plus B units, because this length right here comes from this square, which has a length of A units. This length here has a length of B because it came from this rectangle. Okay, so this entire length here has the length A plus B. This entire side has the length A plus B. The same thing follows here, because this side right here came from dragging this rectangle over. So this has side length A, and this has side length B, contributed from this square here. So altogether, the area of this figure is equal to the area of this, because after all we did was basically combine these four shapes together to get one square. But notice that the area of this square, so it is a square. I know it's a square because this length right here is A plus B, this length is A plus B. So how do I find the length of the square? I multiply side length by side length. Well, this side length measures A plus B, this one measures A plus B. So A plus B times A plus B is the same as A plus B squared. So in conclusion, what I can say is that the trinomial A squared plus 2AB plus B squared is equivalent to A plus B, the quantity, squared. So suppose I wanted to use area models to factor a difference of two squares like this. Okay. So basically what I'm going to do is I'm going to consider the entire square A squared. So I'm going to call this length here A. I'm going to call this length here A. So the area of the entire square is A squared. The area of this entire square is A squared. Now I'm going to take away from it, I want to model subtracting away a square of side length B, which I do here. So once again, I take my entire square of side length A, the area of which is A squared, and I'm going to subtract away from it a square of side length B. So here I have modeled the area of A squared minus B squared, which would be these three regions put together. This piece plus this piece plus this piece is what would be left over after subtracting B squared from it. Just like we did before, I'm going to rearrange these. I'm going to take this square here, place it over here. Okay. I'm going to take this rectangle, place it over here, and I'm going to take this rectangle, place it over here. So now I formed a rectangle, okay, with the same exact area as these three, the square, the rectangle here. Okay, so Notice this length here would be a minus b. Why is that? Well, if you look, it came from over here. The entire length of this square is a, but I've taken away from this length a measure of b, okay, which came from the side length of this square, b. So I'm taking that out. So the only thing that's left over for this length here is a minus b. So that's why this measures a minus b. Same thing with the top piece. Once again, this entire length here measures a. But I took out this piece, which measured b units. So I'm left with a minus b. Okay. And of course, this length here measures b units. Okay. And this one does as well, because it came from here. Okay. So what that means is that if I have a minus b represented in this length, and I add another piece, b, to it, a minus b plus b is just a. So this entire length here measures a. Okay, which you can see from over here as well. Okay. This color plus this color, the length of it is a. So I know that this length here is a. And the length of this is b, so on the entire side, on the width of this rectangle, I have a length of a plus b. So what I just figured out is the area of this region here, this region, minus this, or a squared minus b squared, is actually equal to the area of this rectangle, formed by taking the length a plus b, okay, and multiplying by a minus b. Okay, so what we learned is how to represent factoring special products geometrically. Because the area of a square or rectangle is the number of square units in the product of its dimensions, squares and rectangles can be used to represent parts of algebraic expressions that are perfect square trinomials, or the difference of two squares. You can partition and combine these squares and rectangles into other squares and rectangles so that you can model factorization of these special products.